We're going to test for convergence and divergence of different types of series. For example, if you have the following series, the summation of n squared minus 1 divided by n cubed plus 1, and start from 1 goes to infinity, what's the best ways to analyze this series? Well, it's easier for me to use, for example, comparison test or limit comparison test. Either is fine. It is easy to work with limit comparison test. Why is that? What's the reason behind it? Since when we reduce the terms with lower power, we get a harmonic series. So let me show you. When I try to reduce this, I'm basically getting rid of between n squared and minus 1, between n cubed and plus 1. What happens? This is a constant. It goes to infinity much slower than n squared. The same as constant down here. It goes to infinity much slower than n cubed. So you can reduce this to n squared divided by n cubed, or 1 over n. So this series is comparable to the harmonic series. But we already know that the harmonic series is a divergent series. The summation of 1 divided by n and start from 1 goes to infinity is a divergent series. You can use P series. In that case, P is equal to 1. It indeed gives you a divergent series, or you can use integral test. So let's work with limit comparison test. For the limit comparison test, we are finding the limit of this guy. Let us call it, for example, a sub n, and let us use this guy as b sub n. The limit of an divided by bn as n goes to infinity divided by bn as n goes to infinity, which in turn can be written as the limit of, here you have n squared minus 1 divided by n cubed plus 1 divided by 1 over n as n goes to infinity. Let's do a little bit of algebra to simplify this. This guy becomes the limit of n times n squared minus 1. So we are basically multiplying these two together. Then we multiply these two together, divided by n cubed plus 1 as n goes to infinity. But from the limit, when n goes to infinity, you can divide everything by n cubed to simplify it as much as possible. Or you can basically use L'Hopital's rule. Either is fine. This guy can be written as, so let me show you. The limit of, which is n cubed minus n, you get 3n squared minus 1 divided by 3n squared as n goes to infinity. This guy is equal to 1. But remember that since this is a positive finite number, using limit comparison test, since the limit of an divided by bn as n goes to infinity is equal to a positive finite number, so the convergence, divergence of the summation of an and the summation of bn are the same. Since we know that the harmonic series summation of 1 over n and so from 1 goes to infinity is a divergent series, so as the summation of, what was our series, n squared minus 1 divided by n cubed plus 1 and start from 1 goes to infinity. Just recap what we did. We are analyzing the convergence and divergence for the following series. So since I have n squared minus 1 divided by n cubed plus 1, it's easier for me to work with the limit comparison test. By using the limit comparison test, I can easily see that it is comparable to the harmonic series 1 over n because I can get rid of the terms with lower power. Why? Because n goes to infinity. And n goes to infinity, we can just compare the speed at which these expressions or terms go to infinity. Comparing to n squared, -1 goes to infinity much slower. Comparing to n cubed, 1 goes to infinity much slower. So this is comparable to 1 over n, which gives you the series 1 over n, which we all know it's a harmonic series. As a p-series, this is a divergent series. You can also use integral test to verify that. Limit comparison test says, hey, if you take the limit of an divided by bn as n goes to infinity, and the outcome is a positive finite number, then the convergence and divergence of these two series are the same. But when you're applying the limit, if you use L'Hopital rule, you can easily see that the limit is equal to 1. So when the limit is equal to 1, it's a positive finite number. It means that the convergence and divergence of these two series is the same. But again, since we have a harmonic series, which is divergence indeed, so the series that we have is also a divergent series.